I'm going to give a talk that's perhaps outside the main line of this discussion meeting, but yet I'm going to try and motivate some of it by talking about the entanglement entropy. And I'm going to talk about something that, so let me just first say that this is based on work with Kyriakos Papadimos. And there are three papers that roughly relate to what I'm going to say today, but I'm going to mostly talk about work in progress. But mostly I'm going to talk about work in progress. So let me just try and start by giving you a sense of what's the question that I'd like to ask. And I think this is a question that at least I've become very interested in recently, and I think it is a question that's rather important and may perhaps have something fundamental to tell us about quantum gravity. So the question I want to ask, which sounds like a very innocuous question, is the following. We've checked ADS-CFT now in 10,000 different ways, or more than that, more ways than that. But I have the following question, and I don't know the answer to this, and I'm going to try and say some things about the answer to this, which is the following. If you look at bulk geometric quantities, and an example of such a quantity would be the area that people have been talking about a lot here. Are these quantities given by Hermitian observables in the CFT, or are they given by what I'd like to call functions of correlation functions? And I'll just try and make this question more precise and try and tell you why it's an important question. But this is roughly the question that I'd like to ask. So let me give you an overview of my talk. Since this is a conference on entanglement, I'll start by motivating things with maybe I can put the overview at that side. I'll just start by motivating this question with the Ryu-Takayanagi formula and its relation to state dependence, and then I'll talk about a little bit about the black hole information paradox. I'll talk about state dependence. For the interior, and I'll talk about the construction of the interior in the CFT. And then I'll talk about some other relations, including the fact that, I'll describe this when I come to this. I'll talk about how to preserve linearity in quantum mechanics. And if I have time, I hope I will, I'll talk about the relationship to this other ER equals EPR proposal of Maldacena and Susskind. So let me see how much I can get through. So just to try and explain this question more, let me start by talking about the Ryu-Takayanagi formula, which people talk about a lot, and this whole discussion meeting is on this. And this formula, the way it's usually written, says you look at the area of some minimal surface in the bulk, which is bounded by some region in the boundary, and this area is equal to the entanglement entropy of this region in the boundary with the rest of the boundary. Now the point is that if you look at this formula, and this formula has been checked in many places, it looks like there's an obvious problem, and the obvious problem is the following. This area in the bulk is a geometric, it's an observable. So if you think of quantizing gravity in some canonical gravity sense, then this area is some Hermitian observable. Okay? So in particular, if you have a metric operator, which I can call G hat, which is really an operator, then this area is some functional of the metric operator. Okay? And that means that it obeys various axioms of quantum mechanics, it acts linearly on states and so on. But the entanglement entropy is not a Hermitian observable. It's not something of this kind. So you have here a relationship between something that is a Hermitian observable in the bulk theory and something that's not a Hermitian observable. And so what's going on? And I think that's basically the question that I'm trying to ask here. I should say though in preface that it's not clear to me that the Ryu-Takayanagi formula necessarily says that the answer has to be of this kind. It's not clear to me at least that the Ryu-Takayanagi formula necessarily implies that, although I'll try and give some other evidence that comes from the black hole information paradox that suggests that bulk geometric quantities have to be functions of correlation functions like the entanglement entropy, which is a function of correlation functions in a given state, but are not necessarily given by Hermitian observables. So while I want to say that the Ryu-Taganagi formula doesn't give some definitive answer to this question, I'm just giving it here as a way of motivation and to understand the distinction between these two kinds of things. So let me just say this in one more way. You know, if you think of all kinds of, if you just think of quantizing gravity in some semi-classical sense, and you start with some set of semi-classical solutions, for every such semi-classical solution, the area of the minimal surface is some well-defined observable. Okay? And that means that the area, you know, is a function on the phase space of gravity. Okay? And that's just because, you know, the set of all classical solutions is in one-to-one correspondence with the phase space, and the area is a well-defined function, you know, the minimal area of a surface is a well-defined function on any classical solution, and therefore it's a function on the phase space of gravity. And so if you quantize it, you know, if you quantize gravity, this function lives to an operator which is a hat, and this is the same operator a hat of g hat that I talked about above. Okay? On the other hand, the entanglement entropy is not an operator. I'm sure everyone is aware of this, but let me just briefly review why it's not an operator. You know, let's say we had some operator which had the property that, you know, let me call this operator S hat entanglement, which had the property that it gave you the entanglement entropy of psi acting back on psi. Okay? So let's say you had some operator which had this property. Now you can clearly see that, you know, you can write down a basis of completely unentangled states. You know, if I have some Hilbert space cross HB, there's a complete basis of the Hilbert space which consists of states that are unentangled. Okay? Where VB forms the basis of HB and VA forms the basis of HA. Okay? On all of these guys, the entanglement entropy is 0. Right? And therefore, it would appear that this putative operator, whatever it is 0, because any state, you know, can be written as a linear combination of these basis states. Alpha AB, BA, VB. Okay? And if you use linearity, then this goes through, and because the entanglement entropy in each of these basis states is 0, so it looks like this is 0. Okay? So there's no operator that reduces to the entanglement entropy, whereas it looks like in gravity there is some operator that reduces to the area. Okay? So what is it that's going on? No, the reduced density matrix is not a Hermitian operator. There's no operator on the full theory that gives you the reduced density matrix of something. You know, the reduced density matrix comes by looking at psi and doing a partial trace over something. So that's not what you traditionally call a, you know, Hermitian operator, even though you talk about it often in that way, but it's not really, you know, it doesn't act linearly on states in this way. The modular Hamiltonian is also not an operator. The modular Hamiltonian is also, you know, another example of something which is not an operator. It's given by a log of the density matrix. So the modular Hamiltonian again doesn't have this property. You know, it's not an operator the way you talk about linear operators. There's no Hermitian operator that corresponds to the modular Hamiltonian in a state. And this proof will basically, you know, say this. So okay. So yes. Yes, sure. It's an approximation. I don't think this is very well. Maybe it's relevant here, but I don't think it's very relevant here for the following example. For the following reason, you know, let's say you consider the following state. Okay, this is the state which looks like in the CFT, which looks like this plus beta E2. So this is the state in the CFT which corresponds to a linear superposition of two states with very different energies. One of them has energy E1, the other has energy E2, and corresponding to every energy eigenstate, you can associate some temperature which is beta 1 and beta 2. Okay? Now, if you measure the area in this, so, you know, the geometric intuition here is that you have a superposition of two geometries. With probability alpha squared, you're in geometry this one, and with probability beta squared, you're in this geometry. If you measure the area, then quantum mechanics tells you that, you know, with probability alpha squared, you get the answer A1, and with probability beta squared, you get the answer A2. Okay? Now, the entanglement entropy doesn't have a way of reproducing this probability distribution for you. Let me say here, though, that, you know, it is true that in this state, if you look at a large N CFT, it is true that if you look at the expectation value of the area, which is alpha squared A1 plus beta squared A2, then it's not hard to show that this indeed is the entanglement entropy of the state, up to exponentially small corrections, which you can estimate actually e to the minus n squared in the large N CFT. Okay? or e to the minus central charge in the large n CFT, but n square for the n equal to 4 super angle theory. So you might want to say that the expectation value of the entanglement entropy of the area is equal to the entanglement entropy, but conceptually this is still a little dissatisfying because the entanglement entropy is not the expectation value of some Hermitian observable either. Now I should say it may be the case that there's a version of this formula that says that the expectation value of the entanglement of this area or coincides with the expectation value of some other Hermitian observable in some classes of states. So if you can identify some classes of geometric states for which the entanglement entropy coincides with the expectation value of a Hermitian operator, then you might be able to write down a more precise version of this formula. But I just want to say that from a conceptual viewpoint, there's this question here that on one side you have something that's an operator, and on the other side you don't have something that's an operator. And as I said, I think it's possible in this particular case, at least my intuition is that it should be possible to lift this this relation to something that holds as an operator relation. Although I don't think it's been done, but I think it should be possible. But I'm going to give you another example of a situation where it looks like this is not possible, where it looks like you have a geometric observable which is really not reproduced by something that's a Hermitian observable in the CFT, but looks like it's a function of correlation functions. So at least is this question clear, this distinction between Hermitian observables and functions of correlation functions. Yes.
I thought this equality can be thought of as, let's say I'm talking about ADS3 CFT.
Yes.
In which case the right hand side, the entanglement entropy can be thought of as 2-point function of some special operator.
Okay, but the 2-point function is still not a Hermitian operator. It's a correlation function. If you were able to write this down, then you may be able to write down something that says the expectation value of A is equal to the expectation value of this 2-point function. So if you can show that the entanglement entropy is always some expectation value, then you would have a chance with some relation of this kind.
So are you saying that in the general dictionary of ADS CFT for correlation functions also there is some kind of a problem?
No, I don't think so. I'm not saying that. No, you can have correlation functions on the left matching to correlation functions on the right. But the area is not a correlation function. The area is what in semi-classical gravity you would think of as an observable, which has probability distributions and so on.
Think of this area also as a geodesic, length of a geodesic connecting 2 points of the long.
Yes, but if you think of this kind of state, for example, then there's no geodesic that connects this. Now the answer is that you look at the area and with some probability you get this answer, and with some other probability you get some other geodesic length. So the area has more than that. Not all states correspond to well-defined geometries. You can think of a superposition of geometries, and then you have to tell me what you mean by this side. Maybe you mean the expectation value, and there may be some. I think there's a good chance actually that if you write expectation value on this side and restrict the classes of states in which you're taking the expectation value, then you will find that this is true.
But a single local operator cannot capture the entanglement.
You don't need a local operator, you just need a Hermitian operator. Now, nowhere in this did I say that there's a local operator. I just said there is a Hermitian operator that lives in the CFT that captures this. So I'm never invoking locality here.
But the 2-point function, the reason why we have 2-point function of this operator is to bring in that notion of non-locality. And this is a
Yes, but non-locality is not the key point here. The key point here is whether you have linearity or not. So the key point here is whether you have linear action on a set of states, or if you have non-linear action on a set of states. Let me say a little more. This will become clearer as I say so. So this is just for motivation. I'll say a little more about other kinds of operators, and this will become clearer. Yes.
So a 2-point correlator acting is not linear, or is it?
Well, a 2-point correlation function is not that's an expectation value. So 2-point correlation function is a product of 2 operators is linear. That's fine. A product of 2 operators is linear, but the expectation value of a product of 2 operators is not, that's not a linear observable.
But in Gautam's example, he was saying area and then the twist operators at 2 distinct points.
So you might have a chance in saying area is equal to something O of x1, or you might so maybe this is the relation that you're saying this operator here is equal to a product of 2 operators on this side, and it's also true that in certain states when you take the expectation value of this, you get the entanglement entropy. So if you were to phrase the relation in this way, then that would be a well-defined linear relation. If you were to phrase the relation by saying that area is operator 1 into operator 2, that would be a well-defined relation. But phrased this way, it's not a well-defined linear relation.
Isn't the more defined way phrased as the partition function of the
sorry,
I mean, the area is not traced as area, it's traced as the partition function.
okay, okay. Maybe you can get through this, but can I just I just want to make a distinction here between a relation of this kind and a relation of this kind. This is my main point is not to say is not to discuss how this can be. I think this can probably be made precise, and we can discuss how it can be made precise. But I just want to give you an example of a situation where you won't be able to write down an operation of this kind. And I want to point out that there are these two kinds of putative dualities you can have. One of which in which you have something where the geometry emerges as a function of correlation functions, and the other in which the geometry emerges as a set of linear operators. And we can discuss more maybe at the end of the talk. So again, I want to emphasize that I'm not saying that this formula by itself tells you that the answer is this. It may not. There may be a way to phrase this formula in this way, and we should discuss that more. But as it's phrased, it suggests that this is the answer, and I'm going to give you some other evidence that suggests that this is the answer. Okay, good. So let me immediately talk about some other geometric quantities. And let me try and good. So what are these other geometric observables that look like they don't have an interpretation in terms of boundary CFT operators? And these observables are as follows. So these think of a black hole in a CFT. Okay. You can think of the black hole as being formed from collapse, but the details of how the black hole formed are not important. And the question we would like to ask is, if you measure the field, so let's say you have some scalar field, or if you think of the metric, if you measure the field inside, can you write this field inside in terms of some linear operator that lives in the boundary? And there are some subtleties here which have to do with the fact that you don't have gauge invariant local operators, and so this field inside is not really a local operator. It has some Gauss law tails. You can detect its action from far away because you don't have gauge invariant local operators in quantum gravity, but that subtlety is not important for everything I'm going to say. And what I'm going to try and tell you in the next maybe 20 minutes is why this field inside looks like it doesn't have a representation in terms of a linear operator that lives on the boundary theory. And if that is the case, then either you have to, but it does have a nice representation in terms of functions of correlation functions. And so, that leads to a rather interesting kind of situation where either you go ahead with this and you try and see where it leads you, or you basically accept that there's no interior for a black hole, but it doesn't look like there's a reason to do that because it doesn't look like this leads you to any contradictions. Okay, okay, good. So let me just try and outline very quickly what's the reason that this doesn't work, and what are the precise operators that I'm talking about. Let me try and make this operator, this thing a little more precise. So if you quantize this field, if rather than just speaking of the field, if you break this field apart into modes, then you can introduce some tortoise coordinates. So you introduce tortoise coordinates so that t goes to infinity at the horizon, and there's this tortoise coordinate r star, which in my convention goes to minus infinity at the horizon. So this tortoise coordinate roughly looks like log of r minus the distance. There's some Schwarzschild radius, and if you go near the horizon, there's some more precise formula for this tortoise coordinate, but near the horizon this roughly looks like log of r minus rh. And this tortoise coordinate in the convention I'm choosing, as I said, goes to minus infinity. Now it's convenient to introduce these Kruskal coordinates, which are well defined across the horizon, and these Kruskal coordinates are defined by r star plus t into 2 pi by beta, and this beta is important to make sure this metric is smooth in these Kruskal coordinates, minus t into 2 pi by beta. Okay, and this horizon is given by v equal to 0. Now, if you quantize this field just from a bulk perspective, then you see that you have two different kinds of modes. If you're close to the horizon, then things start looking like plane waves in these r star and t coordinates, and basically like plane waves in 2 dimensions. So it looks like you have two different kinds of modes. There are modes which correspond to, if you quantize this field, let me call this region 1, and let me call this region 2. Okay. If you quantize this field, then it looks like, you can write these modes which look like a omega into e to the I omega beta by 2 pi plus b omega v to the I omega beta by 2 pi plus function conjugate region 1. So let me just explain this. If you think of this capital U to the I pi beta by 2 pi, this is just e to the I omega into r star plus t. Okay. So this is just same as e to the I omega into r star plus t. And it's easy to check that if you go close to the horizon or close to v equal to 0, then these are the solutions of the wave equation irrespective of the mass of the field and irrespective even of what kind of interactions you've given it. So even if you have a massive field, you take it close enough to the horizon, the mass and other interactions drop out, and this is what the solutions to the wave equation look like once you're close enough to the horizon. And in these crucial coordinates, they look like this. Okay? Now, let's say you try and quantize this field in region 2, okay, inside this region, then it looks like you have to quantize it in the following way. Once again, you would introduce left and right movers, and once again, if you look at solutions of the wave equation, they have this form and this form. But this coordinate u, this guy, is actually continuous across the horizon. U is continuous. I'm running out of space here, but u is continuous. Okay, whereas v goes to 0 and then comes out on the other side as some negative thing. Okay, so for whatever you write that multiplies u, you need the same variables. By 2 pi. Okay, but on the other side here, you need some b twiddle operators. And if you notice, if you realize that what plays a role of time here is actually this tortoise coordinate r star and not your original t anymore, then what you see is that you need something that looks like, again multiplying a destruction operator, okay, plus let's see. So I change the sign here even though this is still a destruction operator. Okay, so this is just some wave expansion if you look at this wave expansion. And now you should demand that if you have a smooth horizon, what is the condition that you need for a smooth horizon? The condition that you need for a smooth horizon is that the 2-point function across the horizon should have a certain universal form as you get the 2 points close to each other. Okay? And it's easy to derive. I won't go through this in very great detail. But if you look at the regime where v1 goes to v2, 5 v1, 5 v2. Okay? Let me put some derivatives to get rid of. Let me just differentiate this with respect to v to get rid of the u term. Okay. And it's easy to prove that this has to have the form v1 minus v2 squared if the geometry is smooth. Okay. So this is simply the statement that if you look at a 2-point function of fields as they come close to each other, as you go to the ultraviolet and the points become very close, there's a universal form for the 2-point function, which is basically just fixed by the geodesic distance. And if you differentiate that a couple of times, you can prove this. Okay, I can give you a more precise formula if you like in d dimensions, but roughly this is the form of the formula. Let me write a twiddle here because I've skipped some terms in the transverse directions and so on. But this is the form of the formula. So is this clear? The demand is that if you have a geometry in the UV, the behavior of 2-point functions is completely fixed. It's completely fixed, and that behavior of 2-point functions is just 1 by x1 minus x2 squared, regardless of what kind of interaction you have, whatever else you have. Just the fact that you have some UV fixed point tells you that this has to be the behavior as v1 goes to v2, as you take 2 points very close to each other. As you go far away, of course, you can have different kinds of behaviors. Okay. Now from here, it's not very hard to derive that you actually need correlations between these b twiddle operators and these b operators. Okay. And this is just in some sense, this is a local version of Hawking's derivation of entanglement behind and in front of the horizon. But you can do Hawking's derivation just by looking at this 2-point function, writing down this mode expansion. And you see that if you write down this mode expansion, you get something that looks like yes. Yes, that also becomes irrelevant. That becomes irrelevant, if you try and write down the wave equation in this form, box. So you have a 1 by root minus g, okay, and this root minus g vanishes. So you have something that looks like d mu g mu nu d nu phi is equal to say lambda phi cubed.
I can see that gets redshifted away
right.
Near the horizon.
That's right.
In that kind of calculation, but this stuff that you have written 1 over v1 minus v2
Yes,
squared,
that's also true if you go yes, but if you go very close, if you take 2 points to be very close, then you still expect that that's the case. If you have a well-defined field theory in the ultraviolet and you take 2 points to be very close, then you expect that the 2-point position space correlator should still have this form. Irrespective of what you did, as long as if you have some nice UV fixed point, which is at least which then you expect that the 2-point correlator is basically fixed regardless of what kind of interaction you had.
But from the point of view of this MIT model, say ADS4 going to ADS2, etc., what do you expect at that end?
These are 2 points which are just across the horizon, which are very close to each other. They're here. One is here and one is here. They're almost on the light cone.
You're saying they don't pick up an anomalous dimension?
I don't think so. I don't think you should expect that there should be an anomalous dimension.
Because you're deep in the IR.
You're deep in the UV. These are very close to a light cone. Locally at least these things are, you excite something here and you measure it very close to a light cone again.
But from the point of view of the CFT,
Well, so right now this is a semi-classical analysis. All I'm saying is if effective field theory holds here, then the light cone structure of 2-point correlators is basically fixed. Way things behave close to a light cone is basically fixed. I don't think you can modify this too easily. If you want semi-classical effective field theory to hold in this region, how you realize it from the CFT is a different issue. But if you're you shouldn't have that things near the light cone, you modify the light cone structure of correlators too much. You may modify them if you go really close. If you try and go within Planck distance of the light cone, then you may try and modify it. But as long as you're at a distance which is smaller than all other scales in the theory and much larger than Planck length, you expect that this behavior should hold. Now, actually, it's easy to prove that from here, you basically are forced to the fact that B and B twiddle have correlations. And that comes about as follows. If you just take this expansion and you sandwich it inside a 2-point function, you'll see you'll get some terms that look like B omega, B twiddle omega into V1 by V2 to the I omega beta by 2 pi plus something else that looks like B omega dagger, B twiddle omega dagger plus other such terms. Okay, but let's just focus on this term. If you look at this term and you see that if you impose the fact that I'll just verify this for you, 1 by 1 minus e to the minus beta omega, then you see by doing this contour integral that in fact you will get a log of 1 minus v1 by v2, and when you differentiate it twice you'll get this 1 by v1 minus v2 squared. Okay. So you can verify this, and this is I think a nice derivation of the entanglement that Hawking found between right movers behind the horizon and in front of the horizon, but done entirely locally and by just demanding that the 2-point function has a certain universal form near the light cone, without talking about trans-Planckian physics and trying to trace rays all the way back here. Okay. But in any case, the summary is, and this is a summary that's well known from many other derivations, including Hawking's derivation, is that you need new modes behind the horizon, and these new modes have to be correlated in a state that has a regular geometry with the modes in front of the horizon in a very specific way. And if this correlation breaks down, then you have trouble and you get some firewall. In fact, you can also prove that for locality to hold, these B's and these B twiddles must commute at least as long as these frequencies are distinct. Okay. And so the question in this information paradox, and a lot of this recent debate around these AMPS arguments and whether black hole interiors exist in the CFT or not, has to do with whether these B twiddle omega operators, which are these operators behind the horizon, have a representation in terms of CFT operators or not. Okay? And now I'm going to try and tell you that it looks like these guys do not have a representation in terms of ordinary Hermitian linear operators in terms of the CFT, which are globally well defined everywhere. But if you look at a given state and at excitations about that state, then they do have a representation, which I'll try and outline concretely. And then I'll try and outline concretely what are some of the consequences of this construction in terms of this particular issue of preserving the linearity of quantum mechanics. Okay. So at least is this question clear, that you need some operators behind the horizon that need to be correlated with guys in front of the horizon in a very specific manner. Okay, good. So now let me. The momentum in the transverse directions, it doesn't matter quite for this solution. This is still always omega into r star plus t for the same reason that all these interactions and the mass drops out. However, I cheated a little bit. If you really do this analysis in d dimensions, you find two things. You find that actually physics becomes ultra local in the transverse directions. So if you have some other transverse directions, then physics becomes ultra local in those directions. And so I can write down a more precise formula. That's why I wrote a twiddle. I dropped the other directions. But there's actually a delta of x1 minus x2 in the other directions in this limit. But for now, those are just spectators, and that's not important, so I don't want to go there. Okay, this is something, yeah, that was also pointed out by, in this paper on this covariant Buzzo bound by Maldacena and Cassini and Buzzo, how this physics becomes ultra-local. So it's an interesting fact actually, but it's not relevant to what I'm saying here. Okay, good. So now let me before that say how these B omega operators are realized in the CFT. So the way these B omega operators are realized in the CFT is in terms of modes of generalized free fields on the boundary. So roughly, the statement is that these B omegas go to some O omega by root G omega, but this root G omega is some normalization factor that is totally unimportant for what I'm saying. And what are these O omegas? These O omegas are modes of fields on the boundary that have the property that if you look at a correlation function, then this correlation function factorizes. So the stress tensor is a good generalized free field on the boundary. So these are operators that have the property that their correlation functions factorize, but these operators don't obey equations of motion. So the stress tensor is a good example of an operator that has this property. It's a generalized free field. So is trace of f squared. And these modes B omega, which are propagating modes in the bulk, can be identified precisely as modes of these kinds of operators, which are normalized in a particular way. This normalization has been the subject of some study, but is not important, again, for what we are going to say. Okay, this normalization is what gives rise to this thing called the transfer function that people who are familiar with this literature might have seen. Okay. And now, what I'm going to try and show you is that while this is a perfectly well-defined map, it looks like there is no good map in terms of CFT operators for these B twiddle operators, if you make some reasonable physical assumption. So let me try and give you that proof. This is a version of a proof given by Marolf and Polchinski, which I believe we've been able to tighten a little bit and iron out some things, but the idea is essentially the same idea that they outlined. So the idea is as follows. Think of, if you could define some such operator, this B twiddle operator, then you would also be able to define a number operator for the infalling observer, which I'll call NA following Marolf and Polchinski. And this number operator has the following form. 2 into B twiddle omega, B twiddle omega, B omega, B twiddle omega dagger, plus another term of this kind. Okay. So this is just the number operator that you define by doing the usual Bogoliubov transforms from Rindler to Minkowski modes. The other term is precisely of this kind. It just involves an interchange of the B's and B twiddles. Okay. So this is a well-defined number operator that tells you what the infalling observer will measure, how many particles the infalling observer will measure. Now, the claim is that you can't have a linear operator in the CFT that can measure this number operator for you. And the claim is based on the following physical conditions. So on the one hand, you want to say that energy eigenstates are smooth. Okay, so this is the first statement. So if I look at the projection operator, okay, onto the space of states where I measure a non-zero number operator, okay, then this is 0, or is approximately 0, plus some 1/n corrections. So this projection operator projects onto the space of states, tells me the probability that I'll measure a non-zero number operator for this. Okay. So if the horizon is smooth, then you expect that the infalling observer will see no particles, and therefore this projection operator on all energy eigenstates gives you 0 plus 1/n, and the assumption is that energy eigenstates give rise to smooth horizons, because energy eigenstates behave a lot like the thermal ensemble or like the microcanonical ensemble by the eigenstate thermalization hypothesis, and we believe that those things correspond to smooth horizons. So this is the first physical assumption. The second physical assumption is that Schwarzschild number eigenstates are not smooth. Are not smooth. And the reason for that is that if you look at the vacuum of this guy, the vacuum of this guy involves some thermal distribution of Schwarzschild number eigenstates, And so presumably, an individual Schwarzschild number eigenstate is not smooth. And it's true, semi-classically, if I make a projection and I really tell you that I'm in a given Schwarzschild number eigenstate, then effective field theory would suggest that you will encounter a firewall as you go through the horizon. So if you're in a given, and this is true in Rindler to Minkowski space as well. If you project onto a given number eigenstate in Rindler space, then it's true that you don't get a smooth spacetime. So this is the statement that I'm running out of notation, but let me call this NS. I'm sorry about this NAN and NS, but this is a number eigenstate. This is some order 1, plus 1 by n corrections. It may be smaller than order 1, but it's some, there's a non-zero probability, or there's a high probability that you will measure, particles if you fall through the horizon in a Schwarzschild number eigenstate. Okay? So are these two physical assumptions clear? And now I'll try and prove that they're contradictory. It looks like this doesn't work. Okay. Are there any questions about these physical assumptions? Or? Yeah.
So define PA again.
PA is the projector onto is the probability, gives you the probability that you will measure non-zero occupation of NA. It's the projector onto all states which have non-zero values of NA. 1 minus the projector onto the vacuum of NA. Okay. Good. So the proof goes as follows. We know that number operators of Schwarzschild, Schwarzschild number operators are actually close to energy eigenstates in the infinite end limit. So if you look at the free theory, then energy eigenstates are also eigenstates of the number operator. So if you take some band of number operators or some band of free eigenstates in some region, then it's true that you can write every energy eigenstate. Let me put some notion, is some f alpha plus some remainder, where this remainder is suppressed by 1 by n. So what I mean to say here is that you look at the energy eigenstate at a given value. This energy eigenstate with a given energy can be written as a superposition of free energy eigenstates, or as a superposition of Schwarzschild number eigenstates in a given range. I don't have to go arbitrarily high up and down. If I allow myself to go arbitrarily high up and down, I would have no need for some remainder term. But the statement is that you look at free eigenstates in some interval, and these combine these combine to give you the interacting eigenstates. In principle, there are contributions from eigenstates that are higher as well. Okay. Free energy eigenstates that are higher as well, and these are what I'm calling R alpha, and these are what I'm calling F alpha. Okay. So is this equation clear that I have free energy eigenstates in some band, and the interacting eigenstates are given by the free eigenstates in this band, or some operator that lies within this band of free eigenstates, plus some remainder that captures the effect of things that are arbitrarily high in energy. Okay. Now, it's also true, and you can prove that these free eigenstates are approximately orthogonal since the energy eigenstates are orthogonal. Okay. However, it's a very general theorem in quantum mechanics that if you look at the value of a projection operator, if you have two states, psi 1, psi 2, which are almost parallel, then you look at the expectation value of any projector in these states, you can prove the bound more precisely, but the fact is that the difference of expectation values of these projectors has to be order epsilon. Okay. So if you look at two states which are almost parallel, then the results of any physical experiment in this sense, in that if you look at the expectation value of a projection operator, have to be close to each other with an order epsilon. You can prove a more precise bound, but what's important here is that you take two states which are almost parallel, and the results of any projection also are almost the same. As a result, this means that you look at this guy, the same projector that we had here, and this is approximately the same as F alpha plus some correction, but that doesn't matter, plus some small correction. And now if I look at the trace over the microcanonical ensemble, which involves doing a sum over alpha and dividing by the number of energy eigenstates, that's the same as doing a sum over this and dividing by a number of energy eigenstates, dividing by the width of the microcanonical ensemble, plus some 1 over n correction that I can forget about. But because these guys are just orthogonal combinations of these Schwarzschild eigenstates, this is the same as and that's order 1. Whereas on this side you started out with something that was order 0. Okay. So clearly you have a contradiction because you found 0 is equal to 1. Okay, so there's a problem. Okay.
So how many states are there in the range?
These are well, these are exponentially large number of states, but the range is order 1. The states get so there are if you look at the free theory, it has exponentially large degeneracies at any large energy, and there's the number of free states at a given energy is e to the n squared. Now, so what I want to do here is I want to sum over an order 1 range of energies to get the microcanonical ensemble, and I want to sum over some order 1 range of free things. The total number of states is very large. This number d is e to the n squared. But that can't help you because you're dividing by this d. So what matters is the average. There are a large number of things, but the more states you include, the averages should become better and better. So it looks like you have a contradiction, which is 0 equal to 1, which you don't want. So what's the resolution? How do you resolve this paradox? There are some other arguments that were given by AMPS, and I won't go through them. This is one of the strongest arguments that was given by AMPS. Okay, so we have a construction of these B-twiddle operators, which however avoids the issue because it doesn't, you can't do this change of basis because it doesn't correspond to a linear globally well-defined operator in the Hilbert space. So I'll just outline our construction, and then I'll say a few things about the properties of these operators. So our construction is as follows. Start with an equilibrium state of the CFT. Equilibrium state of the CFT is defined as a state in which expectation values, at least for necessary condition for an equilibrium state, is that expectation values of operators don't depend on time. Things are time translationally invariant. So an energy eigenstate is a good example of an equilibrium state by this definition, but you can also take other more combinations of energy eigenstates, and things still won't depend on time, provided these combinations are suitably chaotic. Okay? So an equilibrium state is a state in which correlators are time translationally invariant. So just to make this more precise, A of 0, A of t is equal to psi. For any observable, any ordinary observable, any coarse-grained observable, any product of these generalized free fields that I was mentioning earlier, any reasonable low energy observable satisfies the property in the state that you can translate things by t and nothing changes. So it looks like this is the time. Now our construction is start with an equilibrium state of this kind, and now excite it a little. Excite it by turning on some unitaries or turning on some sources or turning on one of these generalized free field operators that I mentioned earlier. So you can turn on some product of these generalized free field operators that I mentioned earlier. You can't turn on a huge amount of energy. I'm not going to allow you to add an energy n squared to the system, but you can add some order 1 amount of energy. And the statement is that this O twiddle operator, which is going to correspond to the B twiddle, let me write B twiddle since B twiddle operator on the state psi is defined to have an action which is the same product of guys into a B omega dagger into some factor, which is not important. But the fact is that this B twiddle is defined to have this action, okay, on this equilibrium state and on all reasonable excitations of this equilibrium state. By reasonable excitation, I mean you take one of these generalized free fields, the stress tensor or trace of S squared, you take some of its modes, you multiply them together, or if you like you can take local operators, multiply them together, but you don't take n squared of these guys. You don't take a huge product of these guys that will let you go from the black hole to the vacuum or something like that. Okay? So you make some reasonable low energy experiment. These are the kinds of things you can measure in effective field theory, and the statement is that I want my B twiddles to satisfy this equation. Okay? Now if you look at this space that's formed by taking this equilibrium state and by acting on it with some product of generalized free fields of this kind, this space gives you some smaller dimensional vector space in your big Hilbert space, and that smaller dimensional vector space I can call H psi. Okay. So H psi is a vector space which is given by the span of operators acting on psi, where these A stands for any product of these guys of this kind. Okay. So this gives you a small vector space, and this tells you the action of this operator on the small vector space. Okay. But I can always find an operator that has this action simply by solving these linear equations. And these linear equations always have a solution, provided that if I take any of these products, it doesn't annihilate the state. So that's the condition for the consistency of these linear conditions, is that a product of small generalized free fields shouldn't annihilate the state for any such product. And it's easy to prove that if you take a generic high energy state, then indeed you can't annihilate it by a product of operators of this kind. Not all states have this property. For example, Schwarzschild number eigenstates do not have this property. They can be annihilated just by O omega dagger O omega, because it's an eigenstate of that. So O omega dagger O omega minus some constant annihilates the state. Okay. So those are not the kinds of states I'm considering here. There are other states, and generic states are not annihilated by this product. Okay. And if that's true, then you can solve these linear equations and construct a representation for B tilde omega on this space H psi, which consists of an equilibrium state and some excitations about the equilibrium state. Okay. So if you want a picture, you have some big Hilbert space, and you can write down operators that describe, you have some big Hilbert space, HCFT. In the middle of this big Hilbert space, you have some equilibrium state psi, and you have some small Hilbert space, which is H psi, which consists of excitations of this equilibrium state, and you can write down an expression for the number for this interior operator acting on this equilibrium state. However, if you go to some other state which is very far away from this state, then the operator that you're using changes. It's a different operator. Okay. So that's the picture that you get from here. Are there questions about this picture? I want to say a little more about these properties now in the last 15 minutes. But there's another field. No, it's not a question of another field. It's a question of going. So this is a picture of the Hilbert space. Okay, the Hilbert space is some space of the CFT, and in this Hilbert space you have some point which corresponds to this equilibrium state, which has this property. And about this point, I've now made some excitations which correspond to the kind of experiments I would do in effective field theory. And now I've told you, look, about this space I can define some operator which tells you what an observer inside the interior will measure, what some interior observer will measure. If I go to some other very different state, then it's some other operator in the theory. It's not the same operator evaluated in a different state. It's really a different operator, because if you try and solve these equations about some other very different state, you'll get a different solution for them. Okay. So this is the property. Now this might seem usual, but but however I want to say, and it's true, that this is somewhat it is somewhat unusual. Usually when you try and write down yeah. The B tilde is defined in its psi, or that's right. So you can't extend it infinitely. At some point, the equations will become inconsistent. So you can't extend it to cover the whole space. So you can define it about one equilibrium state, about another equilibrium state, about a third equilibrium state, and I'll show all those. I'll just show in the next 10 minutes that all those definitions are consistent. So you can define it in the neighborhood of any equilibrium state, but you can't. At least we don't know how to extend it to the full Hilbert space.
I could have to say psi and psi prime,
Mm-hmm.
and then I have some intersection of H psi and H prime.
Actually, usually you don't have an intersection of H psi and H psi prime for two states that are in equilibrium. So you can't have an intersection of two states, of excitations of two states that are in equilibrium.
You can't reach the same state
From two equilibrium states, not from two you can take a combination of many equilibrium states, and then it's true that you can get these kinds of dependencies.
Even different equilibrium. I mean,
Many different equilibrium states.
individual states of the same equilibrium. And
Right.
Same ensemble. Then of course they are very close together.
Well, they're close together, but they're orthogonal. You see, if you take an energy E, and energy E plus e to the minus n squared, this is actually orthogonal. And even though they look like they're very close to each other in terms of energy, but they're actually orthogonal eigenstates. So in principle, if you take two equilibrium states, all of which are drawn from the same energy band, two typical equilibrium states are generally orthogonal. You can't take one equilibrium state and excite it a little bit and go to another equilibrium state. If you could do that, then this definition would immediately become inconsistent. And the reason is, if you excite it, it's out of equilibrium. So you're not usually able to take something, act with some unitary, and get some other non-equilibrium state.
Extract some something from that state plus e power minus n square,
Yes.
and that could then go to equilibrium, right?
What? If you extract, okay, let's talk later. Okay, good. Okay, good. Now the thing is that you know we've done this, and this operator satisfies linearity within this small h psi, and you can say that's good. But someone can come along and start asking questions of the kind that I asked at the beginning of this talk, where I said, you know, what happens if I take a superposition of two different equilibrium states which are very far away? You know, I take a superposition of a black hole at some temperature T and another black hole at a temperature 10 T. You know, then how do you, and then I start doing excitations about this. You know, how do you ensure that your operators act correctly on superpositions of this kind? And this is one of the primary criticisms that's been made of this construction, that it doesn't look like it will account well for superpositions of this kind. And I'm going to now try and show that it actually does work well for superpositions of this kind if you take superpositions of small numbers of equilibrium states. Okay. So just to make this precise, you know, usually when people talk about operators of this kind that don't behave like ordinary linear operators, an acid test for operators of this kind is to entangle the system with a pointer. With a pointer. Okay, with a pointer is just some other system. And if you entangle a system with a pointer, you can see that this immediately starts telling you, based on some very simple physical considerations, that your operators have to act linearly, on at least on superpositions of small numbers of states. And how does that proof go? Now, let's say I consider some pointer which has m plus 1 states, okay, and I take vi pointer psi I CFT some ai 1 to m plus Vm plus 1. I've just picked out, so I have a pointer which has m plus 1 states, so it may be some qubit system which happens to have m plus 1 states, and I'm choosing to consider the following entangled state of the CFT, where all of these psi i's are different equilibrium states. They may be at the same energy or may be at different energies. They're different equilibrium states, and I've entangled them with a pointer in this way. Okay. Now, you know, you would like, what's the intuition that corresponds to this? The intuition that corresponds to this is that you have a big black hole. You know, there's some black hole here, and some observer jumps in with a small apparatus. Some observer who jumps in with a small apparatus, and he makes some measurements, and in making those measurements, he entangles the CFT. You know, he entangles the CFT with this pointer, and he can produce a state of this kind by doing something. You know, if he has a small pointer in his hand, he can produce a state of this kind. Now, you would like to ensure that, you know, someone in the interior can't send messages to this guy. Okay. So you'd like to ensure that if you act with a unitary made of these tilde operators, then, you know, action of a unitary on the state does not change the density matrix of psi of the pointer. And b tilde, but I've exponentiated to get a unitary. You know, you can only actually act with unitaries. So it's exponential of b tilde or some linear combination of b tilde, some Hermitian combination of b tildes. So that's why it's unitary. Yes.
How is b tilde defined? I mean, is it a b tilde defined on one equilibrium state?
Right. Right. So whatever the b tilde that you define on the state has to satisfy this. So, you know, the challenge for our construction is to say, you know, find a b tilde that ensures that it doesn't, you know, it doesn't have this property. So I'll say in a second how the b tilde is defined.
No, but you gave me a construction for a particular equilibrium state.
Yes.
And now you've got a whole bunch of different
Yes. 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 So I'm actually going to say that just this requirement forces you to define it. You know, gives you a forced definition on this combination. So I'm going to derive how it acts on this combination. So the physical condition I'm going to put is that u tilde of psi doesn't change the density matrix of the pointer, and, you know, the statement is that, you know, degrees of freedom, whatever this u tilde is something that still acts entirely within the CFT. Okay. So I'm also going to say that u tilde of psi basically is, you know, whatever the action of u tilde is here plus some action of u tilde on these guys. Okay. So the undefined thing here is the action of u tilde on this sum, because the action of u tilde on all of these equilibrium states should be defined using the same principles that I had here. but I haven't defined for you how the action of util lies on this sum. Okay. But you can easily check that if the density matrix of the pointer is not to be altered, then you're forced to the conclusion has to be given by it has to be given by linear action. If you don't want the density matrix of the pointer to be altered, then you're forced to this consideration. I can prove it easily, but I'm running out of time, so I won't do the proof. But it's very easy to persuade yourself that if you compute the density matrix later, first before, and it's some density matrix, it's vi into a squared plus vi into vm plus 1 into ab, and you compute it afterwards, then you're forced to this relation. So you have to have linearity if you don't want to have this kind of superluminal propagation. But the thing is that this is fine. There's no problem in making this consistent, in ensuring that this twiddle acts correctly on a superposition of a small number of equilibrium states. You see, if I take a small number of equilibrium states, then it's still true that I can't get by acting with any element of the algebra. So I can simultaneously impose the action of this twiddle on excitations about all of these equilibrium states, and there's a single linear operator that stitches together all of these actions and acts correctly also on small sums of this. Okay? So there's no contradiction, and the reason is this. If the psi i's are independent equilibrium states, then it's true that you still can't annihilate the psi i's by acting with any element of the algebra, and therefore this set of linear equations I can impose them separately for each equilibrium state, and I can stitch them together. So there's no problem in making sure that your operator acts linearly on a small superposition. Okay. Now where do you start seeing something more complicated happen? The place where you start seeing something more complicated happen is if you entangle, now I've come to the last part, which is the relationship with ER equals EPR, is when you entangle the system with a very big pointer. What if I take the CFT and I entangle it with another CFT that has as many degrees of freedom as my original CFT? Okay. Then you find that you have some trouble. On the one hand, you would like to ensure that if I take an entangled state of two CFTs, some maximally entangled state, okay, and I allow this to settle down, then you still get some smooth black hole geometry on both the CFTs, and so you would still like to impose these linear equations, which are that O twiddle on on this psi entangled, this is now an entangled state of both the CFTs, is given by A omega dagger psi beta omega by 2. Okay. But if you now demand that your O twiddle acts only on the first CFT, okay, acts only on the first CFT and doesn't act on the second CFT, then you find that you will be simultaneously led to, if I write now psi entangled as sum of psi I CFT1, psi I CFT2 into some Vi, okay, and I go through that logic and I insist on demanding this equation, which is that the action of this U twiddle is entirely within the first CFT, then I'll end up with a relation that says that U twiddle on each of these guys, on any such guy, is given by A, is given, well, I'm sorry, I'm shifting a little bit between the O twiddles and U twiddles, but they're just related by an exponentiation. That's because it's easier to write the action of an O twiddle. One can write the action of an U twiddle also. And that this holds for all states, all sorts of equilibrium states psi I and excitations of these. But you can see that this is you can very easily see that this becomes an overdetermined set of equations. And that's because you have all of these eigenstates of the CFT which are entering into this entanglement, and you have excitations of these eigenstates by products of simple O's. Okay. So you're trying to specify the action of O tilde on too many states, on more than a dimension of the full Hilbert space, and clearly that's inconsistent. You can't try and specify the action of O twiddle on this. But there's a simple solution, and the simple solution is that you allow O twiddle, you still impose this relation, which is the equation that, which is our fundamental relation, but you don't try and impose the relation that O twiddle acts entirely within one CFT. Okay. You allow it to act also on the other CFT that you have entangled things with. Okay. Okay. If you do that, then it's very easy to solve this set of equations, because now you have a big Hilbert space and you're just solving a small set of equations. You don't have to solve this set of equations. You don't have to solve this set of equations. Okay. So, but this is saying that the interior, so what's the geometric picture that's coming out of this? I'll just end on it, I'm done. Yeah, just 1 minute. What's the geometric picture that's coming out of this? The geometric picture that's coming out of this is that you had one CFT, and you have a black hole, okay, in this CFT. Now you entangle it, you couple it with some wire to another CFT. Okay. And now the interior of the black hole consists of degrees of freedom from this CFT. And the reason for that is that, as I just pointed out, this O twiddle is forced to act on the second CFT as well. It's forced to act on the Hilbert space of the second CFT as well. So we are seeing that, but this is precisely this ER equals EPR, conjecture that Maldacena and Susskind made. And so we are seeing that, if you take the CFT and you entangle it with some other big system, with some other system that has the same number of degrees of freedom as a CFT, as the original CFT, then you're forced to a situation where the interior of the black hole actually consists of degrees of freedom that come from the second CFT. There's no way to avoid that. So this is, in some sense, giving you a precise version of how a wormhole opens up. And the wormhole has opened up in this way, that you jump behind this horizon and you find that you're actually manipulating degrees of freedom here. Okay. So it looks like even though you have these unusual operators, it still looks like this is consistent with some other intuition that you get from other places, which is that if you entangle two big systems, this wormhole opens up. Okay. Okay, so I'll stop here. I'm almost out of time. Let me just summarize and say some things in summary. I think that this question I started out with initially, I think, looks like an innocuous question. Are geometric quantities in the bulk defined in terms of Hermitian operators, or are they more general functions of correlation functions? But I think it's a very interesting question. And I think in this entire discussion of the black hole information paradox, we are being led to a situation where it does look like, what look like observables in the bulk are actually described as functions of correlation functions. However, no bulk observer doing simple experiments using effective field theory can determine or can detect any violation of quantum mechanics. Okay? And what is more, you get these surprising predictions of these wormholes forming if you try and entangle things and you try and test things at a very high accuracy level. But this is something that I think is qualitatively new, because we are coming to a situation where, in some sense, quantum mechanics for the bulk observer is itself emergent. Now you have a situation where these observables are being given by more complicated observables on the boundary, but nevertheless it looks like quantum mechanics holds for any bulk observer doing simple experiments, and so it looks like you have a situation where quantum mechanics itself is emergent. Now it may be that this whole story is wrong, but it may also be that it's something very interesting, and this discussion on the information paradox is leading us to the situation where it looks like quantum mechanics in the bulk may itself be emergent from the boundary. Okay, so I'll stop here.
There was a lot of interaction, so until there are emergency questions, and I think I suggest we head for lunch. Everybody is welcome to lunch. Another announcement is that if you are persistent enough and you stay on long enough, there is also some dinner arrangement from 6:45. That is to encourage people to discuss with our speakers. So depending on how persistent you are. Another thing is that the Chandrasekhar lecture by Rob is going to be in the physics auditorium, not here. So just be aware of that. So please, let's head off for lunch.